I warmly welcome all of you in the first session of this CIMPA School on recent advance in combinatorics and its applications. So I'm going to request Professor Andrea to come and present his lectures, start his lecture series. The main topic of her lectures will be on the coloring and labeling of graphs. Please.
Thank you very much. Good morning to everybody. My name is Andrea Semaničová-Feňovčíková. I come from Slovakia. I am very happy that I am here. I am very happy for inviting me, and I hope that you will enjoy my lectures. So the title of my course is Coloring and Labelings of Graphs. During my talk, I would like to tell you something about magic squares and magic graphs, then something about anti-magic graphs. Then I will speak about colorings induced by anti-magic labelings, and at the end, I will tell you something about irregular assignments. My goal is not to present you some theorems and proofs. My goal is to present you some techniques how to find labelings for some specific graphs, because this can help you when you decide to work in this area. This can help you to obtain some results, to know how to obtain some labeling schemes for some small graphs. Then you will be able, if you will know how to do it, then you will be able, maybe it will help you in some other projects. So my goal is to show you the beauty of graph labelings. This is my favorite topic. And I hope that after my talk, you will also say that you like it. Don't worry, it is easy to understand. And I hope that you will enjoy it. So let's start with magic squares. Magic squares, when we would like to start with magic squares, we have to go very back in the history. So we can find the first magic square in Chinese literature in many years before. So there is a very known legend about the turtle of Lo Shu, and this turtle should help people to bring them happiness and to prevent there was a flood during that time, and it should help the people to protect them. And this is the pattern that is given on the top of this turtle, and this is what we call magic square. So here we will have a definition. What is a magic square? Magic square of order n. It will be okay when I will stay here. Okay. So magic square of order n is array with n row and n column, and we would like to put numbers from 1 to n square to this square such that if you will check what is the sum of numbers in every row, in every column, and in both main diagonals, you will always get the same. So my goal now after the first part of my talk, now you will be able to construct such magic square. So we start with a very simple example with motivation. So we have the 1 entry. So what should we give there? Yes, I told you that it would be. Okay, and now we will try to construct magic square of order 2. We have 2 rows, 2 columns. Can you see? Yes, it's over. And now, what we would like to do, we would like to put the numbers from 1 up to 4, just every number must be once. And according to symmetry, it doesn't matter where we will give number 1. So say it will be here. Okay, you don't see it. And now, give here number 2. How many possibilities we have? The 2, according to symmetry, we have 2 possibilities. So, the number 2, you can possibly put here. But is it possible to put there the other numbers? Because now we have the sum of these 2 numbers, 3, and 4 plus 3 is 2 plus 3. So this is not possible. We cannot do this with way. So the other way how we can construct it is possibly to distribute the numbers 1 and 2 in such a way. And according to symmetry, This is only one way. And now it is easy to see that 3 plus 2 is 5, 1 plus 4 is 5, but 4 plus 1, 3 plus 1 is 4, and it is not going to the other column. So this is not possible. So it is not possible to construct magic square of order 2, and this is the only exception. For the other orders, you can always find magic square of order n. So let's start with magic square order 3. We will use numbers from 1 up to 9. And now we would like to put these numbers to the square. So maybe my first question is, what will be the sum of the numbers in every row, every column, and every in both main diagonals? So how we can evaluate? So what must hold is every sum must be the same. So if you would like, it would be great if you will cooperate. So what must hold? It's easy. 3 times which number? Lambda, yes, I didn't. Equals to? Yes, it's that, yes, it's exactly how we evaluate the constant. So the value of the constant is 15. Yes. And now we would like to distribute numbers such that we will obtain number 15. And one way how we can do it is we can make or we can try to write number 15 as a sum of 3 numbers. So how many possibilities we have? These are all the possibilities. Yes, we have nothing else is possible. And now look, my question is, okay, which number we have to give here in the middle? So this number in the middle is on the both main diagonals, is in one row and in one column. So it must be in these sums, it must be counted 4 times. Is that some number? 5, yeah. So if you have magic square of order 3, number 5 must be always in the middle. And now, check the numbers in the corners. Yeah? So numbers that are placed in the corners, they must be in this partition how many times? So it is in column 3 times. Yes. So and which numbers from these numbers from 1 up to 9 are mentioned here 3 times? 2, 8, 4, and 6. Yes, so we see that even numbers must be always in the corners. And it is not complicated then to find the distribution. Yeah? And my question is, what do you think? How many? We know that in the middle, there always must be number 5. Even numbers must be in the corners. And after isomorphism, how many possibilities we have to construct magic square? Is it possible to find another distribution of numbers? What do you think? Yeah, when we check the sums, okay. So how many possibilities we have to find such magic squares? What do you think? Is it possible to find another magic square of the 3? Up to isomorphism. No. This is the only way. Yeah, you can rotate it or but up to isomorphism, this is the only case. So we have exactly 1 of order 1, no of order 2, 1 of order 3. And now we are just coming to something interesting. If I ask magic square of order 4, we have 880 magic squares of order 4 up to isomorphism. Of order 5, more than 270 something millions. Yeah. So of course, it is not possible to show you here all constructions. And my goal is to show you some constructions just for some of them. And so I will show you my favorite constructions. One is for the case when n, the order is equal to 4. And the other one is for n is when n is 4. Okay, so let's, I will not explain why it is working. I will only show you that it is working. And how to find the distribution of numbers. So let's start with magic square of order 4. And what we do, we put the numbers in such a way. Yeah, so we have a trivial distribution. We start from 1 up to 16. Of course, it's not magic square. It is possible to evaluate the magic constant. And what is here interesting is to see that the sum of the numbers on the diagonals equals exactly to this sum. So we just need to make some distribution of the numbers, make some slopings, such that we will keep the position of the numbers on the main diagonals, and we will just make some transformation with the other numbers. So what to do? So we will divide the square into 4 parts. We will draw 2 lines, and then what we will do? Then highlight the 4 elements, entries in the middle. And then in every subpart, you will also color the resulting numbers such that you will obtain a chessboard. Yes, so here we highlight number 1, number 4, 16, and 30. Yes, so make something like that. In every part, draw to obtain a chessboard. And now we will do some swapping. So we will swap only numbers that are colored this yellow color. And what we will do? We will swap numbers that are here we have a symmetry. Yes, so they are symmetrical according to this one. So we swap these 2 numbers. Then we will swap these numbers. Then we will swap 4 and 13, 17, and 10. And this is a construction. I will not deal with the fact why it is working. Just feel this fact is working. You will obtain a magic square of order 4. Yeah, and you can check that the sums in every row, every column, and in both diagonals is 4. 34. Yeah, so this is one way how you can do it. So you know how to do it. So what shall I do? You remember? What we have to start with what? Yeah, we have to divide it into 4 parts. Then we have to highlight the 4 middle elements, and then we will color the other elements such that we will obtain the chessboard. And now we will do swapping. Yes, number 1 will come here. It will be the position will be changed with number 64. 10 will be changed with 55. 34 with 31, and so on. And when we do it in this way, we can obtain magic square of order. Okay. So this is very easy construction how we can do it. So we will repeat it. Yes, it's easy. Divide into 4 parts and draw or highlight chessboard and then make swapping. So you can do it. So you can come home and tell somebody, oh, I will give you, I don't know which money is a lot of for you, and euros or more, yeah? And you can tell, give me paper and I will draw you magic square. It looks complicated, but if you know how to do it, it's not complicated. So this is when we have order divisible by 4. Now, what to do when we would like to obtain a magic square of odd order? So we already know construction. We know that there is only one for this or magic square of order 3. And now, if there's some construction for general text, of course there is not only one, there are many of them, and one of them is based on the following. So first, place numbers like this, 1, 2, 3. Just so we have a diagonal. Then we will draw, put numbers in the second diagonal. 6, 7, 8, 9. Yes, so we start with distribute numbers in this way. And now we will shift some numbers, because here you can see that here we have some empty space. And how we will fill this empty space? So the way how to do it is again very simple. So what we will do? So consider this line and shift this line to the opposite line. So this means that we will shift number 1 to this hole. Yep. And then we will shift this line from the right side to the left side. So the number 9 will come to this hole. And then what we need to do next, from the top, we will do the same. We will shift the numbers. So number 3 will come to this hole. Here we identify this line with the bottom line. And then the last step. And we are done. So this is, again, very simple construction of that works. Yeah, and we can check that the sums are always 50. And you remember how to do it? So what shall I do? We will start with the main diagonal. So the first diagonal will be the diagonal that contains these numbers. Yes, so we will put numbers here. Okay, so the first diagonal, then second, third, fourth. Sometimes this method is also called pyramid method, because look, if you have odd order, so here is something that looks like pyramid. And now we will do the shifting. So the numbers from the left side will fill the holes on the right side. So we will do it. From the right side, numbers will go to the holes on the left side. And from the top, we will shift numbers to bottom. And from bottom, we will shift numbers to the top. Yeah, and you have COMSATS. I hope that you believe it's on that line there. Okay. As I told you, magic square exists for every positive integer except again and n. If you are interested in such constructions, one quite recent book is this book, Magic Squares. The history just to the year 1600, yeah. There you can find many other constructions. So you have many constructions that you can find. Maybe you will find something that is more interesting for you, something that you really like. But for us, magic square is just something that we will use later. Many times we use this type of labeling to construct another bigger structure. Of course, you can find magic squares not only in mathematical books, you can find them also in some in art. This is an engraving from Albrecht Dürer from this is engraving Melancholia, and maybe it is not visible, but here you can find this detail, and this is magic. Or you can find it also when maybe some of you visited Spain in Barcelona, and there is a Passion facade of Sagrada Familia from Joseph Maria Subritas, and here you can find something that is not really magic square, it's a semi-magic square. Yeah, it has some properties that the sums are constant, but we do not use numbers from one to we somehow modify. Yeah, but we can find it. And also, where you can find magic square, or maybe it's better say semi-magic square, you can find it also in Faust from Johann Wolfgang Goethe. So here you have the text from Faust, and here is the corresponding semi-magic square. So people are fascinating, and as I thought, not only mathematicians, also the other. Yes. Why is for semi-magic? Yeah, look, because semi-magic means that the sums are constant, but you don't use numbers from 1 up to 9. Then you have the number 0, 10. That's why it's called semi-magic. It's not the same, so maybe it's like I didn't check, 15. Yeah, here on this side it's not the same. Yes, so it has some partial properties. Okay, so we have magic squares, and how we can extend it. Yeah, so trivially we can ask, if we have a magic square, is it possible to make some extension of it? Trivial extension is to obtain a magic rectangle. So what is magic rectangle? We will have some arrays with, say, m rows and columns. We would like to distribute numbers from 1 up to and such that the row now the sum of the numbers in every row will be constant. Sum in every column will be constant. Of course, this constant will be distinct. And how we can do it? So, for example, here we have a magic rectangle with 3 rows and how many? 9 columns. Yeah. So you can check the sums in every row and every column, and you can see that these sums are constant. And it is known, this is very old result, that the magic rectangle exists if and only if we have at least 2 rows and at least 2 columns, n times n, so the product of m and n must be at least 5. And very important information is that m and n must have the same value. And this will guarantee us the existence of such magic rectangles. Magic rectangles are used very many times, because if you would like to construct a bigger structures, so you can obtain something that's a property that you require, and then you will just glue magic rectangle to that. So it will help you to obtain a lot of results. Okay. And now, another, then, natural extension is that if we have a magic square, it is possible to have magic cubes or magic hypercubes. So what is magic cube? Here we have an example of magic cube of order 4. So magic cube of order n is you have an array 3 times 3, 4 times, or in general n times n times n. We put numbers from 1 up to n cube. Every number is used exactly once. And what we require that the sum of the numbers along any row, any column, any pillar, and the four main space diagonals is a fixed column. And so we have a structure that is like a generalization of the concept of magic squares, and it was proved by Trenkler. She was my teacher. You will listen to his name many times today. And he proved that magic cubes exist for every positive integer exponent. Okay, and now maybe you how we can come from magic square to magic graph. The connection is really very simple. So look, we have a magic square, and what we will do? We will denote the rows of this square in such a way. So the first one will be R1, the second row R2, third R3, and all we denote the column C1, C2, C3. And now consider the complete bipartite graph K3, and denote the vertices of this complete bipartite graph in one bipartite set by C1, C2, C3, R1, R2. And now we will label the edges between these vertices. And how we will do it? Look. Here we have edge between the vertices R1, C1. So we will label this edge with the number that is in column C1, row R1. So we will put number 2. Oh, I started with number 1. Sorry. So here we'll go the number 2. But in my example, I started with number 1. So number 1 is in row 2, column 3. So we will assign number 1 to this edge. Yes? Edge joining the vertices R2, C3. Then number 2 is in row 1, column 1. So we will assign number 2 to this edge. Now number 3. Number 3 is here. So it is row 3, column 2. Row 3, column 2. So we assign number 3 to this. So is it easy how we assign the numbers? And 4, 5, 6, 7, 8, 9. And that's all. And now, what we have? We have something that we call label graph. Yeah, we assign numbers to the edges of the graph. And what is the interesting property of this labeling? Check and tell me what is the sum of the labels edges incident to this vertex. What is the sum? 50 for this vertex. For 50 for C3. And for the vertices on the bottom. 50 for all of them. Is it surprising for us? Why? It was contracted from magic square. Yeah. What we know? Look, what is the sum of numbers that are assigned to the edges incident to vertex C1? Yeah. So it's 2, 9, and 14. So as these numbers are in the same column or in magic square, so their sum must be constant. Okay? So this is the way how we can obtain magic, we call it magic labeling from magic square. And this connection between magic squares and magic graphs was first time mentioned by Czech mathematician Jiří Sedláček in 1963. So he showed that there is a correspondence between the magic square of order n and called here supermagic. I will explain it here. Labeling of complete bipartite graph K and I. Supermagic is mentioned here. So super big. Later we will use labeling that will use distinct numbers for we will assign numbers to the edge. Or we will use consecutive numbers to that we will assign to the edges of the graph. And if the numbers are consecutive, or some mathematicians say that or require that we will start from one after the number of edges, in such a case we call such labeling super. So this is one way how you can obtain the labeling for a graph. And trivial question is, if we have a labeling of a graph, is it possible to obtain magic square? Yeah, is it possible to construct the magic square from labeling, required labeling of complete bipartite graph? Is it possible to do it? What do you think? So let's check this example. Yeah, we have, it's too small, but maybe you can see. So this is magic labeling of complete bipartite graph K3. So you can see that this, for every vertex, we call this is the weight of the vertex, is again 15. And we construct corresponding, now I will call it a square. So you can see the correspondence is trivial. And now, my question is this structure, what we have here, is this magic square? What's the problem? Diagonal. Yeah. So when we will come back, we cannot guarantee that this will work also for diagonals. Sometimes it can happen, yeah, but not for all labelings. So somehow to come back is not possible, or you will just get some partial. So this is one way. Okay, so let's start with the definition, with the formal definition of the magic graphs. We will consider only simple graphs. So graph without a loop, multiple edges. For beginning, consider that we have just connected graphs, but it is not necessary to restrict on it. So we say that graph is magic if it is possible to assign numbers to its edges. We label the edges of a graph with distinct positive integer. So in general, when we have magic labeling, it is not required to have consecutive numbers. Yeah? We just have distinct numbers. are assigned to the edges of the graph. And what we require is that the sum of labels of edges incident to each vertex is the same. For every vertex, the sum is the same. This constant sum is called magic index of this labeling. And here we have a labeling F. So here is the formal way how we can write what is the magic. And when we have the additional property that the edges are labeled with consecutive integers, in such a case, we call such graph Supermagic. So we have one additional property. Here we have graph K5, and it's a magic. This labeling is a magic labeling. Then we assign distinct numbers to the edges of this graph. Yes. And when we check the magic index, for example, for this vertex, it is the 1s, 113, 18, 14. So you can check it is for I'm using this picture many years, so I hope that there is no typo. Okay. So if you will check the sum of the labels for every vertex, the weight of every vertex is the same. This labeling is super because the used numbers are not consecutive. Okay. And here we have example of Supermagic labeling. This graph. Again, we have a graph. It has 12 edges. So we use numbers from 1 up to 12 that we assign to the edges of this graph. And again, we check the weights of every vertex. Yes, this graph is irregular, so for every vertex, we evaluate the sum of 4 numbers. And you can see that for every vertex, the sum is the same. Okay. And now, we have a couple of terminology. Yeah? Because some authors, like Stewart, he define max, he is using the notation of Supermagic graph or Supermagic labeling if the edges are labeled with consecutive positive integers. So we can start with number 7. But the other authors, for example, Hartzell-Leveringer or Shu and Lee, they call graph Supermagic, yeah, the same notation, but we have different definition. When the used numbers for labeling the edges are numbers 1, 2, 3 up to number 2. Don't worry, with the scale, you will need many times when you will deal with label graphs. And because sometimes it seems that we do not have enough words because everybody is using the same notation. So when you read the paper, you have to first start with the definition, because then you can think, oh, something wrong, but the result is for different. And so you have to check really properly the definition. Of course, if you have regular graphs, these two definitions are regular. Hey, it's easy to prove that if you have a regular graph that is Supermagic, so you can start with any number. Okay. Now, my question is, consider that we have a Supermagic labeling. We use the definition of Hartzell-Leveringer. So we assign numbers from 1 up to number of edges to the graph. And now my question is, what is the magic index of the Supermagic graph of any? You know, if you have a Supermagic graph, so try to find the value of magic index. It's not complicated. Somebody can help? You can answer. It is. Okay? So what we do? We assign numbers from 1 up to number of edges to the graph. So how many times every label is used? Twice. Because edge has how many? Two times. How many vertices has one edge? 2. Okay? So every label of every edge contributes twice to the vertex weight. something else that could help us? It's similar, like in your case. What you will get, then you evaluate the sum of the numbers from 1 up to the number of edges, multiplied by 2. So what you get? Yes. This magic index multiplied by number of vertices. So we have this very simple formula for evaluating the Supermagic index when we consider the definition by Axel and Jezný. Yeah? We evaluate the sum of numbers from 1 up to number of edges multiplied by 2, and this equals to the number of vertices multiplied by this magic formula. So this will give us some very simple sufficient condition, necessary conditions for existence of magic or Supermagic labeling. Okay, and we consider the Supermagic definition by Stuart. What will be the magic index? This says that we label the edges of a graph with consecutive numbers starting with the 8. It's the same. The idea is the same. Yeah? Every label is with twice, so the sum of these numbers multiplied by 2 must equal to the magic index multiplied by number of vertices. Okay, so we have this one. Yeah? So it's easy. Again, very simple calculation. Of course, when n is 1, we obtain the previous. Okay. And now, we know that magic square exists for every integer n different from 2. So immediately from this result, we have that complete bipartite graph K and N is magic, or we can say Supermagic, for every positive integer except 2. And the question is, what about the other graphs? And this is solved. So if you would like to do that, you don't need to do it because we have a complete characterization. Yes. We know characterization of regular magic graphs by 2, and there are, in 1988, there were published independently 2 different characterizations of magic graphs. One is by Jezný, and one was published by Jezný and Trenkler. And for Supermagic graphs, the situation is much more complicated. There are now some construction or characterization of Supermagic complex graphs by Stuart and Jarko Ivančov. He's also from Slovakia. He's also from Slovakia. He's my teacher, and I'm very happy that he was my teacher. So he gave a characterization of Supermagic regular complex multipartite graph as Supermagic. So we have, yes, sir. This is starting from any number. These graphs are regular, so. And now, if you are interested in a lot of results about this type of labeling or any other type of labeling, you can read the survey of Gallian. It's updated almost every year, and you can find many results. So if you decide that you will work in this topic, so first check what is known, and you will find there also inspiration for the other work. Okay, now I would like to show you how we can obtain magic labeling of any graph, such labeling. So we will use Jezný and Trenkler characterization of magic graph. So they prove that the graph is magic even only if the following 2 conditions are fulfilled. So the first one, every edge of a graph belongs to one factor. So what is a one factor? One factor is a spanning subgraph of a graph such that every component of this one factor is either one regular or two regular. So what does it mean? Every component of this graph is either a cycle or is isolated edge. Okay? So the first condition is that every edge of a graph must belong to a one factor. And then the second condition is that for every pair of edges, you have to find a factor, one factor that separates these two edges. What does it mean? The two edges are separated by one factor. So it means that either it means that only one of these two edges belongs to one factor, or if both belong to one factor, one is in the cycle path and the other edge is the isolated edge of this factor. And how to use this construction to find a magic labeling of any graph, if it exists. Then if the labeling for a given graph does not exist, so you will be not able to find this. Okay, so we will do this now. But I think that you are hungry and you don't want to do it. Okay, so have this smaller input. Okay, or you would like to do this one. Everybody's hungry, yes. So start with a smaller page. Yes. If somebody wants, you can try to do it. If no, I can maybe some yeah. If you would like, it's not easy to work with this one because you will say, oh, it's very complicated for this one. If somebody wants to try to do it, I don't have to. Or if no, we will work with this one. We will continue with this one. Okay. So what we will do? We will start with a graph at the beginning, no edge label. Say every edge has label 0. And now what we would like to do? We would like to at the end have such situation that every edge will be labeled with a different number. So first what we will do? We will start with any one factor. So say for example this one, and we will assign number, say 1 to every edge of this factor. So what will happen? Originally, when all edges were labeled with number 0, so the weight of every vertex was 0. And now, what is the weight of every vertex now? For every vertex. Yes? So we have, say Semaničová-Feňovčíková labeling, yes? The weight of every vertex is the same. And now, what we will do? We will find another one factor, for example, this one. And now, what we will do? We will add or we will increase the label, the origin value by some value. And how we will do? So first we have to think that we have cycle path and we have this edge. And then we would like to guarantee that after this operation, the sum of the weights of every vertex will be the same. What we have to do? Okay, so every edge here, we will assign some number. This is trivial. And say, if we will assign number 1 to every of this edge plus 1, so what will happen? The weight of every vertex will be increased of these vertices of the cycle will be increased by number 2. So it means that we have to assign which number here, or increase which, what we have to add here, plus 2. And it is always like that. If you will assign, you will get some, or increase some value of cycle path with some number, you will give, or you will increase the label of the edge of the isolated edges twice with this number. And of course, we would like to do this in such a clever way that we would like also make the edges are labeled with distinct numbers. So here for this one is easy. We can assign number, for example, plus 2 for every. We can increase every label of this cycle path by 2, then we will increase the label of this isolated edge of 4 is 2. So what happens? What will be how we increase the value of the weight of the vertex? So this will increase the weight of every vertex by 4. Okay. So what we have this one. Now we still have one edge that is not labeled. Yes, there is 0. So maybe try to find such factor that contains this edge. For example, this. And do the same. Okay? We will increase the value of every edge here in this cycle part by some number. And the edges here, we will increase plus double of this number. Yeah. So what do you recommend to do? Maybe you will choose the 7. Yeah. Is it good to give here 2? One here, one no. Why? Because we will have the same number as here. So it has no sense. 2 no, because this edge is labeled by 2. So you can always find some sufficiently large number to do it. And so what I did, I split by 6. And you just need to guarantee that the labels of edges they will be distinct. Of course, this is not how to say you will not obtain the smaller, very small magic index. And so it is not very effective. But we have this one. Okay, so is it the resulting, is it okay or we have to change something? Let me help. It seems that every edge is labeled with this number. Yeah. So different. If you are interested, then we are done. Here is the algorithm how you can do it. Okay, so the first step you start always with number 0. Then in the second step you will find one factor, and it is written here how you have to increase the value or you define a new labeling of the graph. So I will stop soon. I will talk later. So here is the whole algorithm, and I will finish with this one. Okay? I told you that we will work with this one. Of course, it was not. I am sure that you know that it was not obtained using the other algorithm. Next time we will continue. Okay, so thank you for the attention. Do you have any questions?
Any question you want to ask? Any questions? Yes. You didn't say anything about the proofs. Are they just by inspecting just the algorithms?
Yes, I think that now we do not have time to go through the proof. From my point of view, it is better to show you the ways how to do it. Because many times when you see you just see the theorem. So you know that it is working. Then one way is how to obtain it. Yes, in the proof, it's either in the way the labelings end. And of course, the second part, the most important part is to prove that it is working. And I think that here we do not have space to prove it.
So that the main argument would be like the first or
you can find this. I didn't give a proper references for this result, but you can find the proof in the yes. For example, for this one, it is easy to prove. Yeah, so it's like in the steps when I had it. So it was in the step it was proved or showed how you can see that it is working. If you would like to think or find more results, you can do it. At least for this result, the proof is hidden in this step.
Any other questions?
Thank you very much for the lecture. It was very interesting. But I have one question that from the big scales, you have bipartite graphs. And what about the rectangles? Is there any graph?
This is like you use it for another construction. So when you would like to have a graph with some other properties, So this is something like you will divide your big graph into several subgraphs. Yeah, some spelling subgraphs, and one is something that has for which exists a magic rectangle, and then you can construct the graph with bigger properties.
Thank you.
First of all, it's a very wonderful talk. And we do labelings, we construct magical graph with positive unity.
Yes.
So can we do it in positive vector?
During my next talk, I will tell you that you have thousands of labelings. So, but you have to start somewhere. Yeah. So when you are in a new topic, you always. But one way is that you will just start to study one topic. But it is good to have a background in something. And this is one type of labeling. There are thousands of labelings. There's many different properties. And it is good when you know something about this labeling, it will help you for other types. Yeah. So of course, it is not needed to use integers. You can also use real numbers. This labeling is working for real numbers. So why to restrict those integers? It doesn't matter.
Okay, all right. And one more thing. I did not see any matrices. Can we associate matrices to graph labelings or magic?
Magic square is like matrix. Yeah.
And then can we find so it's the idea that can we associate matrices?
At least you have adjacency matrix, and you can assign. You just label the edges of the graph. So instead of writing a number, there is a vertex. I'm writing number. There is edge in the vertex. Writing number 1, so you can give the edge label. So there are ways how you can do it. It's just the way how you like it. Usually, what we do, we give the formula for the labeling. And so you have a label formula, maybe just 1 line, maybe sometimes 10 lines, and then you prove that. Yeah, how is the step? How you obtain the result? You are playing with some small graph. You find out that it is working. Then you try to generalize it. So you obtain the contraction for a bigger graph. Then you write the formula, but then it's coming something that is the most important part. You have to prove it. Okay? And this is something that you ask that where is the proof? And it is the next step what you need to do. But when you are doing research, you can't start with the proof because you have nothing. Okay? So you have to have skills. And what is important, you have to start with small graphs. You have to touch the graph and to see the property, to see how it is working, to see how it works for small structures, and then to try to generalize it. Because when you will not know how it works for small cases, you will be not able to find general results. But of course, you cannot stop that it's working for graphs with 10 vertices. Maybe with 11 it will not work. Yeah, so you have to prove it. Of course, it's the next step. I think that we have to.
Yeah,
you talk about magic sphere and magic cubes. May we think in more generalized space, like magic space?
Hypercubes. Yeah. It was proved by Trenkler.
Thank you very much, Andrea.